Good morning, respected judges. We are Team OCULUS MARINE. We've spent the last few months deeply studying the challenges our scientists face in Indian marine research. The biggest problem is clear. The entire process is still manual. This means our best researchers are spending over 6 hours for a single sample, just counting organisms one by one. This isn't just an inconvenience, it's a fundamental limit on the speed and scale of research our nation can conduct. We believe it's our duty as engineering students to help solve these national problems. That's why we've developed a practical, powerful solution, and today we want to show you our working prototype.
So our working prototype. This is our edge computing module built on Raspberry Pi, which gets a live high definition feed directly from the microscope. The module creates its own standalone Wi-Fi hotspot, enabling full headless operation. This means you don't need a monitor or keyboard. It can be controlled wirelessly from any device in your hand, whether it's a laptop, tablet, or smartphone. Once connected, we navigate to the system static IP. This loads our entire user interface, which is built on Node-RED framework, a powerful environment for creating seamless hardware-software connection. The dashboard has full suite of features, but to focus on our core innovation, we'll demonstrate the two modules we built from ground up. Alright, let's jump into image acquisition. You are seeing the live high resolution feed coming directly from a microscope. To ensure the best data quality, we use configurable burst capture. We are setting the number of frames, and this interval acts as critical stabilization delay to guarantee every image is perfectly sharp. Once we start, the process is fully automated, building our high quality dataset frame by frame, and the dashboard provides real time progress. When the capture sequence is complete, our pristine dataset is immediately ready for the next crucial step in our workflow, image segmentation. Now that our high quality dataset is secured, we move to the next critical step, image segmentation. From the dashboard, we simply select our most recent acquisition folder and initiate the process. First, the system performs dynamic background estimation, calculating a flat field image to correct for any uneven illumination. Next, it uses a sequence of morphological operations to create a binary mask, precisely isolating each organism from the background as the object count increases. The final stage is size-based filtering, which automatically discards small artifacts and noise, ensuring only biological relevant organisms are extracted. This process is intensive for accuracy. The final output is an archive of segmented images and metadata, ready for our classification pipeline. And this brings us to the final step of our prototype workflow, classification. While our Raspberry Pi has been essential for proving our acquisition and segmentation pipeline, it hits a hardware limitation when it comes to running heavy AI workloads on the device. So, we designed a robust hybrid solution. For labs with internet access, the segmented files can be sent to Ecotaxa. Ecotaxa is the world's largest validated plankton database, offering 83 to 89% accuracy by leveraging over 650 million images and completely free for use. It's a powerful tool and perfect online component for our system when internet is available. However, the core requirement of our problem statement is a true embedded system that works completely offline. This has been our main focus and led us to a critical question. Is it even feasible to learn a lightweight yet accurate AI model on low power hardware? To answer this, we initiated the validation test. We didn't just pick a model, we engineered a feasibility study. We fine-tuned a lightweight YOLO V11 architecture on a curated dataset of challenging low contrast organisms, and the results were a major success. Here you can see in the model in action. With high confidence detection on sample organisms, this is a visual proof that a compact on-device model can work. These visual results were backed by hard data. The training convergence, as you can see from the loss curves, was excellent, indicating a stable and well-trained model. Our validation metrics show a high mean average precision MAP, which is a gold standard for object detection. And most importantly, this confusion matrix confirms high species level accuracy, proving the model can reliably tell the difference between classes. This validation test was a critical milestone. It de-risked the most important part of our project. We now have the data-driven proof that our vision for a lightweight on-device AI is not just possible, it's achievable. So, we have proven the workflow with our prototype. We have proven the AI model with our validation study. But on the Raspberry Pi, these are still separate manual processes. You acquire the images, then you segment them, then you would classify on a separate machine. This is why the NVIDIA Jetson is not just an upgrade, it is the key that unifies our entire solution. Its power allows us to take all those proven separate steps and merge them into one single seamless real-time pipeline that executes in under 100 milliseconds. Our final architecture is built for performance and reliability. The Jetson acts as a central brain handling everything from multi-interface microscope input to running our final production grade AI pipeline. This pipeline evolves from our YOLO validation test, upgrading to a USAM based detector and a highly optimized efficient net B0 classifier, achieving our target of 96.36% accuracy.
So, we have a powerful technology, but the most important question is, what is the real world impact for India? Environmentally, as our system provides near real-time data, it gives our scientists a massive advantage. They can now monitor the health of our crucial marine ecosystems much more effectively, tracking pollution and the impacts of climate change with greater speed and accuracy. Economically, our solution directly supports the Make in India initiative. It's an affordable, homegrown technology that upgrades existing lab equipment. This reduces our nation's dependency on expensive foreign systems and, as our research shows, delivers a 60 times reduction in the cost per sample. On a social level, this tool breaks down barriers. It makes high-level marine science accessible to a wider range of people. Universities, smaller colleges, and even citizen scientists can now contribute to national research goals, strengthening our entire scientific community.
So, that's our project. Today we have shared with you our research, our technical plan and our prototype. But I want to end with why we did all this. We started a journey not just to win the competition, but because we saw a real problem. We saw our country's brilliant scientists spending hours on work that a machine could do in minutes. We believe their valuable time is better spent making discoveries, not just counting. What you saw today is more than just a project, it's our promise. It's a promise that we, the next generation of engineers, are ready to work on the problem that matters to our nation. We have built the foundation, we have proven it works. With your guidance and support, we are ready to take this foundation and build a tool that will truly serve India and its scientific community and years to come. We are Team OCULUS Marine and we are ready to get to work. Thank you.